Welcome grade 6 to your e-lesson. Today we are going to start our new chapter, which is chapter number 7, Forces and their effect. In this unit, all the major forces are described in detail. We use the word force in our daily lives countless times. It means that the energy required to do any work. Some sight words of this chapter are force, gravity, ballast force, density, volume, weight, mass, air resistance, and friction. Starting our lesson, page number 90. A force is a push or pull. Some forces only act when two objects are touching. These are called contact forces. Some forces act at a distance. For example, the gravitational pull of the earth holds the moon in the orbit at a distance of 350,000 km. All the pieces of the metal in the concrete in the bridge shown in the photograph are acted upon by forces. This changed their shape. Some pieces are in tension. The forces are stretching them. Some pieces are being compressed. The forces are squashing them. Some pieces are bending because the weight of the bridge. So here some common forces are described, that is the contact forces. As the name suggests, this force requires two objects, for example the force of push or the force of pull. But also there are some forces which act at certain distance, for example the gravity. Gravity is the pull of the earth which holds the moon in its orbit. As you can see the picture of the bridge here, some parts are in tension, means that the edges of the ropes are so tightly pulled like the rope. Some parts are in compression, means they are being squashed and pressed hard, while some are bent like the top rope.
At the end of the last video, I talked about interaction between any two bodies. Whenever two bodies interact, each one of them applies force onto the other. But how do the bodies interact? Interaction between the bodies can be basically of two types. One in which the bodies are in contact with each other, and the other in which they are not in contact with each other. The forces that result when the bodies are in contact with each other are called contact forces, and the forces that result between the bodies when the bodies are not in contact are called as non-contact forces. It's easy to think of contact forces, but it's a little difficult to think of non-contact forces, right? Yes, there are some forces which operate between objects even though the objects are not in contact. We will study more about non-contact forces in the future videos. First, we will discuss contact forces. Suppose that you're thirsty and there is a glass full of water lying on the table. In order to drink some water from this glass, you have to lift the glass towards your mouth. That is, you have to apply force on the glass. How are you applying this force? You are touching the glass with your hand and lifting it. Here, your hand is in contact with the glass. So the force you're applying on the glass is a contact force. Here is an example from the previous video. This player wants to pass this football towards his teammate, who is standing on the other side of the pitch. The player will apply the force on the ball by kicking it. When the player applies force, his foot is in contact with the football. So this force is a contact force. Other examples of contact forces can be pushing or pulling the desk from one point to another point. Here our hands are in contact with the desk. Similarly, pressing the keys on the keyboard, moving a piece on chessboard are some of the other examples in which parts of our body are in contact with the objects and apply force on them. Muscular force and force of friction are the examples of contact forces that we have discussed previously. But is contact between the objects always a necessity for the forces to come into play? Let us find that out. Take a bar magnet and place it on the table. What is a bar magnet? Well, we all know what magnets are. Bar magnet is an artificial magnet which has this shape. Place an iron nail on the same table at some distance away from the bar magnet. Now move this bar magnet towards the nail like this. Keep moving the magnet slowly, closer and closer to the nail, but make sure not to touch the nail. What did you notice? When the bar magnet was sufficiently close to the nail takes a leap towards the magnet and sticks to it. What does this tell us? This shows that the magnet attracts the nail and the contact is not necessary for this attraction. The magnet pulled the nail towards it even though it was not in contact with the nail. The force that this magnet exerts on the nail is called magnetic force. So contact is not required for the magnetic forces to come into play. We call this force a non-contact force. Now, if you bring this magnet close to your iron cupboard, you will get the same results. As you move this magnet closer and closer to the iron cupboard, the magnet will attract the cupboard towards itself and vice versa. However, in this case, it is the magnet which will shoot out of your hand and stick to the cupboard. Are there any other non-contact forces besides the magnetic force? When you release an object, say a plastic ball, from some height above the ground, it just falls on the ground. Why does it fall towards the ground? This is because of the force that the earth exerts on it in the downward direction. The earth always pulls the objects towards it. This force that the earth exerts on an object is called the gravitational force. This force is attractive in nature. That is, it attracts two objects towards each other. When you open a tap, water begins to flow downwards. This is because of the gravitational pull of the earth on water. Now, I want you to tell me, is gravitational force a non-contact force? Yes, it is. We can clearly see from our examples, the contact is not required between the earth and the other object to attract each other. We say that the gravitational force is a non-contact force.
Moving on to the next topic, which is measuring the forces. Forces can be measured by a force meter. This has a spring inside. The larger the force, the more the spring stretches, and the further the pointer moves down the scale. The unit of force. We measure the force in units called newtons, and these are named after the famous physicist Sir Isaac Newton. It may help you to remember that it takes a force of 1 Newton to lift a medium-sized apple. A force meter is often called a Newton meter. When you hang an object on a force meter, the spring stretches and the pointer indicates the weight of the object on the scale. So this topic is about how to measure the force. As we used stopwatch to measure the time, similarly we use measuring balance, which is called the force meter or the Newton meter, to measure the amount of the force. The unit of force is N, and it is named after the famous physicist Sir Isaac Newton. This instrument measures the forces required to lift the weight of the object. It has a spring, a pointer, some readings, and a hook. What you have to do is that hang an object on the hook, the spring stretches and the pointer moves to the certain point or the certain digit. Larger the force of the object, the more spring stretches, and it tells the weight of the object. Next topic is, why do things float? Suppose the object is hung in a beaker of water. Notice how the reading on the force meter is smaller. The object has appeared to lose weight. The Greek philosopher Archimedes noticed this about 2000 years ago. He suggested that the object had not really lost weight, but that it was the water pushing up on it that made it seem as if it had. Archimedes discovered that the amount of the upward push or upthrust was equal to the weight of the water that had been displaced by the object. For example, a block of metal has a volume of 1000 cm cube and it weighs 20 Newton in air. When it is put into the water, the block displaces 1000 cm cube of water, which weighs 10 Newton. The upthrust on the block is therefore 10 Newton, so the metal block will appear to weigh only 10 Newton. Now, summarizing the topic, why do things float here? The important principle is being described, which is known as Archimedes principle. As you've all seen, things like boat floating on the surface of the water. All of the floating object follows a principle known as Archimedes principle. It states that the force exerted by the object immersed or dipped in the water is equal to the weight of the water that particular object has displaced, means that it has pushed out of the way. It means that if you've placed or put anything like stone or rubber in the water, that particular stone or rubber will move the water from its place and take over that certain position. So, the downward force exerted by the stone or the rubber is equal to the weight of the water that stone has moved away. Another example of the same topic, which is given in your book, is that a block of metal which has a weight of 20 Newton in air, when it is put into the water, for example, wooden block has the weight of 20 Newton in air generally. When it's put into the water weighing 10 Newton, the water will exert the same force, that is 10 Newton. So the metal block will weigh 10 Newton. Next is the balanced forces. It states that downward force exerted by the object on the water is equal to the upward force exerted by the water on that particular object. Here a certain condition must be applied, which is the downward force by the object should be less than the upward force exerted by the water on that object to keep it afloat on the water. Next topic is density. Density is the amount of mass in a unit volume of the object. Its formula is mass divided by volume, and and its unit is gram per centimeter cube, or the largest unit is kilograms per meter cube. So here an important thing is that water has a density of 1 gram per centimeter cube, means that water exerts the force of 1 gram per centimeter cube on the object. If any object which has a density less than this will float on the surface of water because it is applying less force, and the upward force is higher as compared to the downward force, so the object will be floating on the surface of the water. Objects having density higher than this will sink in the water because the force exerted by the object will become more as compared to the force exerted by the water, due to which the object on the surface of the water will sink.
We're all aware of the fact that some objects float in water while others sink. Let's look at a balloon. Do you know what makes a balloon float on water? Well, it's the upward force exerted by water that makes the balloon float. To experience this, try pushing the balloon underwater. You will feel an upward force that makes it difficult to push the balloon down. Now release the balloon, it bounces back to the surface. What happens here is that the applied force acts in the downward direction, pushing the balloon down, but the water exerts an upward force on the balloon, pushing it up. This upward force exerted by water on the balloon is known as upthrust or buoyancy, and the upward force is called the buoyant force. Have you ever wondered why an iron nail sinks while a huge iron ship floats on water? Let's see. The iron nail sinks as it is solid and compact with less volume in water, and its density is greater than water. Thus, the upthrust exerted by water on the nail is less than the weight of the nail. This causes it to sink. An iron ship floats as it is hollow, filled with air, and occupies more volume in water, and its density is less than water. Thus, the upthrust exerted by water on the ship is greater than the weight of the ship, letting it float. These examples indicate that the magnitude of the buoyant force depends on the volume V of the immersed part of the body, the density ρ of the fluid, and the acceleration due to gravity G. Thus, upthrust or buoyant force is equal to V ρ G. In general, an object experiences a loss of weight in water due to the upthrust, and it is equal to the weight of water displaced by it. This is better answered using the law of buoyancy, also known as the Archimedes principle, named after the Greek scientist who discovered it. Archimedes' principle states that when an object is immersed in a liquid, the apparent loss of weight of an object is equal to the upthrust, and this is also equal to the weight of the liquid displaced. We see the uses of this principle in our daily lives. Ever caught a fish with a fishing line? When pulling the line, you would have felt the weight of the fish in water is lighter than when the fish has surfaced. Say the weight of the fish in water is 4 kilos. Its approximate weight outside would be 5 kilos. Well, the water level too has come down. This difference in the volume of water level will equal the loss in weight of the fish when in water. That is, the weight of the fish when outside minus its weight when immersed in water equals the loss in weight of the fish. So the loss in weight of the fish will equal the weight of the decreased water. This is because the upthrust or buoyant force is equal to the weight of the decreased amount of water. Thus, Archimedes' principle is verified. Certain technologies today work based on the Archimedes principle. To name a few, the designing of ships and submarines, hydrometer is used to find the specific gravity of liquid, and lactometers used to determine purity of milk. Things to remember. The upward force exerted by a fluid is called upthrust or buoyant force. Upthrust or buoyant force equals V ρ G. Archimedes' principle states that when a body is partially or fully immersed in a fluid, it experiences an upward force that is equal to the weight of the fluid displaced by it.
If we drop a piece of balsa wood and a metal pin of the same mass into the water, what will happen? Will both of them float, or will both of them sink? Or one stays afloat and one sinks? Just by intuition, we can say that the wooden block will float and the metal pin will sink. But if they're of the same mass, why does that happen? Shouldn't both float because of the buoyant force? This happens because of the difference in their densities. But what's density? Look at these two parking lots of the same size. One has 3 cars and the other has many cars. Which one is more dense? This one, correct? Yes. Now look at these two forests. Which one is more dense with trees? Clearly, it's this one. So in the same given amount of space, if there are more things, we say that it's denser. Density is simply the measure of how compact the mass in a substance or object is. If we have to go by its scientific definition, we would say that it's mass per unit volume. In short, it tells us how much mass exists in a given volume. The unit of density is kilogram per meter cubed. Mass is in kilograms and volume in meter cubed. Coming back to our example, why did the wood float and the pin sink? The wood floated on water because the density of the wood is lesser than the density of water. Hence, the upthrust of water on the wood is greater than the weight of the wood. Hence, it floated. But the density of a metal pin is more than the density of water. Though it looks tiny, there's more mass per unit volume within it as compared to water. Hence, the upthrust of water on the pin is less than the weight of the pin. So what can we conclude? If the density of an object is lesser than the density of the liquid, then it will float. And if the density of an object is more than the density of the liquid, then it will sink.